Hello again and welcome to this, the 8th and last lesson in the series of lessons called An Introduction to Functions. My name is Dylan. This lesson is called Translations, and as you will see, we're going to be doing a great deal of graph interpretation. By the end of this lesson, you should be able to describe the effect that different coefficients and constants have on the output value of a function. Remember that many of the examples we've done together have been practical and applicable to your everyday life. Now, in South Africa, we pay value-added tax, or VAT, on many goods and services. And this is a consumption tax based on the value added. Now, when you go shopping, you'll most often see the price tag includes the value of VAT. This is the formula that we use to calculate the VAT on an item. Note that this is a function in which the output is 114% of the original amount. Let's take another look at that formula. We've just seen that the price paid is equal to 114% multiplied by the original price. Now, 114% we can write as 114 divided by 100, which is equal to 1,14. In other words, we can think of 114% as being the same thing as 1,14. So if VAT is set at 14%, we could also say that the price paid is equal to 1,14 times the original price. Now, have you ever noticed that in some shops, the price tag shows a VAT excluding and a VAT including price? To determine the price including VAT, the supplier merely multiplies the original price by 1,14. Let's look at this on a graph. In each case, for 1 unit, 2 units, and so on, the amount excluding VAT is shown by a blue dot, and the amount including VAT is shown by a pink dot. The amount including VAT is the original price multiplied by 1,14. Look carefully at all aspects of this graph. We use discrete points and not a continuous line, as we only buy whole items, like whole CDs. This is an increasing function. As the input increases, so does the output. The domain includes values that are greater than 0, as it does not make sense to buy, for example, -2 CDs. This in turn affects the range, which also contains positive whole numbers. It is quite possible that the value of the tax could be increased or decreased. If, for example, the VAT was 30%, then our formula here would be price paid is equal to 130% times the original amount. Now we know that 130% can be written as 130 divided by 100, which is equal to 1,3. So in other words, 130% would be the same as 1,3. Let's imagine that VAT has been increased to 30%. And we're going to compare the different amounts that we pay according to the different rates of VAT. And I'm going to show you this on a graph. Here we are no longer looking at the price per unit. What we have in this graph is a picture of how the different rates of VAT affect the final selling price based on a range of original amounts. If you think about it, you'll realize that the original amount paid can be any rational number greater than 0. So in this case, we are not plotting discrete points, as in the previous example, where we were working with discrete units. For example, the number of CDs purchased. Remember, when the VAT is 30%, the rate of change is 1,30. And so the gradient of the line is quite steep. When the rate of VAT is 14%, the rate of change is 1,14, and so the gradient is less steep. For the line with the bigger rate of change, the output values change more rapidly for the changing input values. Let's confirm that by having a look at the amounts including VAT for an original amount of 300 Rand. Our input value is 300 Rand, and we can see that when the VAT rate is 14%, if we read this on the graph, the output value is about 340 Rand. When the VAT rate is 30%, for the same input value of 300 Rand, we can see reading off the graph that the output value is about 390 Rand. Remember that as the rate of change becomes bigger, the gradient of the graph becomes steeper. Now, what do you think is going to happen if, for example, the VAT rate were decreased to, say, 10%? You should know by now that as the rate of change decreases, then the gradient of the graph will become less steep. So now let's look at some more graphs. Here we have the graph of f of x is equal to x. And this means that every output value is equal to the input value. So for example, if the input value is 1, we can see that the output value is also 1. Here we have the graph of h of x is equal to 0,5x. Can you see that the rate of change in the initial graph was 1 because the coefficient here of x is 1, while h of x's rate of change is 0,5 because the coefficient of x is 0,5 or a half. Now this graph confirms for us that as the rate of change decreases, so the graph becomes less steep. Here's the third example. G of x is equal to 2x. Again confirming that as the rate of change increases, in this case from 1 to 2, so the gradient of the line also increases. We could say that from f to g, the gradient has doubled. We can picture that the graph of f still passes through the origin, but that it has turned until it has reached the orientation of g. We could also say that from f to h, the gradient has been halved. Now let's look at some more graphs. Here I have sketched the graph again of f of x is equal to x. The second graph I've sketched is p of x is equal to x plus 2. Now for both graphs, the gradient is 1. Remember, the gradient is the same as the coefficient of the x term. In transformation geometry, we often say that the graph has been shifted. So in our example, the graph of p has been obtained by shifting the graph of f up 2 units without changing the gradient. In the formula for p, the constant is plus 2, which indicates to us that the shift is by amount of 2 units, and because the constant is positive, the shift has been in an upwards direction. In the next example, we've plotted the graph r of x is equal to x minus 2. In this case, the constant is minus 2, which indicates that again the shift that occurs is 2 units, but this time it is in a downward direction. We have focused on linear functions throughout this lesson, but remember the growth of bacteria gave us a quadratic function. Now, the addition and subtraction of constants has the same effect for a parabola. The graphs of t of x and g of x have been shown. Now, the graphs are the same shape, but t has been shifted up 4 units to reach the orientation of g. Remember that throughout this series we have been focused on one important idea, that a function describes the relationship between input and output values. And in this lesson, we've seen how coefficients and constants change the output values, and so therefore alter the orientation of a graph, or shift or translate that graph. Now, what's going to happen if we apply 2 changes at once? Well, in the next example, we're going to change the gradient of a straight line as well as shift that line. We start with the graph of n of x is equal to minus x. Now, for the graph of r, we have doubled the gradient. Now, if the graph of r is shifted 4 units up, we would produce the graph of p. The graph of r has been shifted 4 units up while maintaining the same gradient. So, to translate the graph of n to the graph of p, we first need to double the gradient and then shift that line up 4 units. In closing, let's summarize the important points from this block. We firstly looked for input and output values, and so studied the behavior of functions. In other words, we looked at what functions need to do to input values to generate output values. We also learned how to find the rule or formulae on which these functions are based. And actually, this is all that we'll do in algebra in grade 10, 11, and 12. I really do hope that you have enjoyed this series of lessons and have benefited from watching them.